Okay, hello everybody, and welcome to the Aquaterra Energy webinar, Offshore Engineering Challenges for CCS, Considerations for Wells Platforms and Long-Term CO2 Management. My name is Neil Mearns. I'm a market and data analyst at Aquaterra Energy. I've been with the company for just over a year now. I will be the host and moderator for today's session, and we expect the presentation to last between 40 and 45 minutes. This will be followed by a quick 5 or 10 minute question and answer session. So we do expect to finish under the hour. Okay, just to start off by introducing the company in case you're not familiar with us. So we are an offshore engineering company based in Norwich in East Anglia. We are, however, a global company of engineers, analysts and offshore service technicians serving customers and projects all over the world. Our primary business activity is providing services and solutions to the offshore oil and gas industry. So we engineer and design shallow water minimal facility platforms and provide a range of other structures such as drilling templates, tension decks and conductor slot additions. We also offer riser systems and well solution services, including well start and riser and conductor analysis, as well as a range of rental tools and equipment under our Aquaterra Express service. We also provide a range of services and projects in the decommissioning and late life stages. So aside from oil and gas, we now service the energy transition technologies such as offshore green hydrogen, offshore wind, and as you will learn a bit more today, carbon capture and storage. Okay, on today's agenda, we will start off by introducing the role of CCS in this broader environmental context. And we will introduce types and locations of different types of storage sites and engineering considerations for those CO2 storage sites, touching on issues like legacy well re-entry. We will then look at considerations for new and existing platforms for CO2 injection, as well as the importance of long-term CO2 management. So this includes CO2 monitoring, measurement and verification techniques. Throughout the discussion, please remember to submit your questions in the dialog box on your screen, and I will choose a selection to answer at the end of the webinar. So without further ado, I will now hand over to our speakers, Ben Cannell and Stuart Maxwell, to introduce themselves and begin the discussion.
Hi, my name is Ben Cannell. I've got over 20 years experience in the oil and gas industry. I started my career off with Schlumberger. I was there for 6 years, focused on intervention services such as electric line and wireline and coiled tubing. I've been with Aquaterra for over 14 years, predominantly in offshore engineering and subsea services. Various roles ranging from project engineering when I first began to my current role as the innovation director here, with a big focus on energy transition.
Good morning, everyone. My name's Stuart Maxwell. I'm the technical director here at Aquaterra Energy. I've been working for around 32 years. I started in sort of riser and conductor systems, and I've moved on to sort of field developments both here in the UK and internationally. I've been with Aquaterra for slightly over 8 years. Within Aquaterra, I have a sort of pan-company technical remit on all aspects of our sort of products and technology, but I also head up the wing of the company that focuses on offshore platforms. Thank you.
Okay, just to set the scene a little bit before we get into the meat and drink of the actual discussions itself. We're here today because of COP26 and the Paris Agreement and the targets that were set to keep our temperature levels to 1.5 to 2 degrees below in pre-industrial levels. Even this target is going to cause global disruption. There's going to be food shortage disruption, displaced people, potentially crop failures. The world will change, and I think it's important to understand that this isn't a soft target. The target is it's a stretch as well. It's not going to be easy to get there, but it is achievable, and it's important that we try and reach this target, because the consequences of going much over if we carry on the same path are going to be disastrous. Depressingly, we're already a little bit behind the curve, and we've only just begun this journey. So it's important that we get back on track. There's no one thing that's going to solve this climate crisis that's in our toolkit right now. It's important to understand that the Paris Accord tells us quite clearly we can't recycle our way out of this problem. Even if we stop using fossil fuels tomorrow and deployed solar and wind at scale across the entire world, we're so far down through our carbon budget with so much CO2 in the atmosphere already that we will still exceed the targets that we've got out there. And this is due to things like steel manufacture and other industrial processes where there are really no viable options at scale for change. To give you an example, cement, there's really no viable, scalable alternative to cement right now. If it was a country, it would be the third largest CO2 emitter in the world, just behind America and China. So the problems are massive, and this is part of the chemical process, not just to do with the energy involved to produce cement. You can take hydrogen as well. It's a very good point. It's very topical at the moment. A lot of the renewable sources going in right now focus on electron generation, solar and wind. We're used to having molecules available for storage, such as hydrocarbons for our energy on demand. Hydrogen offers a way into that. But even the current hydrogen production, there's produces for industrial processes and agriculture, etc. That generates over 90 million tons of CO2 into the atmosphere every year. We need that, just forgetting about transport or any other means, we need that just for agriculture and industrial processes. That's because most of it is produced through fossil fuels, through grey hydrogen processes. So right now we've got about 400 parts per million of CO2 in the atmosphere. Now the last time those levels were as high as that was over 3 million years ago. And during that period, temperatures were 2 to 3 degrees higher than pre-industrial levels. And the water depths levels were around 15 to 20 meters higher. So that puts it into context where we currently are and where we're heading. Now, one of the big problems with CCS is looking at the scale of it. It's very difficult because some of these problems are going to be more manifest in the future, and some of the size of the numbers are so big it's very difficult for people to sort of comprehend them in your mind. But CCS is an important element of the tools at our disposal to help us achieve the goals of the Paris Accord. It allows us to take action now and at scale to decarbonise industrial clusters. So where we've got hard to decarbonise steel production or industrial processes or even hydrogen production, it allows us to decarbonise these whilst we transition to more sustainable fuels. And this is crucial because a lot of what we're doing in the UK in particular, we're building out massive infrastructure with wind to generate electrons, to electrify everything that we do in our society. And we're planning to build out a huge amount of extra capacity. Now, the problem with these electrons is storage, and when the wind isn't blowing, we want to make sure that we've got power on hand. And industry will change and transition to find molecule storage for that. And one of the answers might be hydrogen, which would potentially allow us to benefit in a similar way to what we have from hydrocarbons, which provide us an on-demand energy resource, which has been hugely beneficial to society in the previous years, and we mustn't forget that. CCS also allows us to deploy at scale negative technologies, which sometimes gets forgotten about what the Paris Accord talks about as well, which is to achieve the 1.5 to 2 degrees, we need to, at scale, have negative technologies. And they talk about some of these currently exist but haven't been proven at scale, and some are yet to be discovered and put to use. So give you some more examples. One of these methodologies is direct air capture, which then goes on to use storage sites around the world. And there's developments ongoing right now. Climeworks and others are doing this. But just to give you an idea of some of the challenges that sort of very embryonic technology uses, is the dilution of that CO2. That 400 parts per million means that it's extremely energy intensive to suck the CO2 out of the atmosphere. Try and put it into context. It's very difficult to imagine what that looks like, but imagine 37 Carrow Road, Norwich City football stadiums. It would be the equivalent, if they were all full, of about 1 million people. So it's like all of those stadiums emptying at one go, and a steward pulling out 11 people from each one of those stadiums as they empty. So you can imagine it's time consuming and very difficult to do that. Trees and plants are a lot better at it than that, and this is where BECCS, you'll hear BECCS mentioned a lot as a potential negative technology and can play a role. It's very important that that comes with sustainable forests and the management and regulation of this, so we don't end up into more problems there. Drax in the UK is a good source of information. They've got a site which has a lot of information on this and how they're trying to convert their business into a negative carbon business. It doesn't come without some controversy, but I think if we just boil it down to what it's actually trying to do, it's disrupting it's using plants and trees and biomass to extract the CO2 from the atmosphere, which they are more efficient at than what we are currently. And it's disrupting the cycle. So it's allowing us to then burn those to generate energy, but capture that CO2 and then lock it away underground. At the moment, it's not really realistic to plant enough trees to take the sort of volumes that we need out of the atmosphere and disrupt agriculture and other areas. So this is an important negative technology that currently exists, but there will be others that come about, and many of them will likely rely on storage sites to lock the CO2 away. So in many ways, the scale of the issue, as I talked about, is enormous, and we're behind the curve collectively on where we need to be with these targets. It can be a bit depressing, to be quite honest with you, about the scale of the problem in front of us and the magnitude of the issues that we face. But there is a big but. I strongly believe that certainly in recent years, there's been a genuine change of heart from people and organisations and governmental bodies that really see the need to change and transition and to tackle these really complicated issues. But importantly, this is an industrial revolution focused around energy, and there will be many, many opportunities that come out of this piece. The key thing is we need to deploy now and at scale, and CCS is part of one of the methods that we can use to help us decarbonise right now. That's the key bit. Next slide, please. So there's many different formations, if you like, that we can store CO2 in. I guess the best place to start is most logical, which is existing depleted oil and gas reserves. So these are useful because they're very well known. So we have lots of seismic data, wireline data, performance data when we've been draining the reservoirs down. And there's the potential to put existing assets such as pipelines and platforms and repurpose them for a new lease of life for CO2 injection. Some of the sizes of these range from 10 to 100 square kilometres, and just to sort of give you some context, the Northern Endurance CO2 project, one of the Track 1 projects in the UK, the formation that they're looking to store the CO2 in is about the height of the Shard and about the size of Manhattan Island if we were to look at it subsurface. So it's an enormous structure under the seabed. And one of the other big advantages with using these existing sites is the speed in which that you can come to a conclusion about whether or not a particular site is going to be economic and technically viable, because you can do a lot of this work from a desktop study with the data that's available, where it might not be available for new sites. But the scale is important. Size really does matter, and some of the bigger sites, saline aquifers, for example, I think will play a really key role. So some of these saline aquifers are absolutely enormous. You know, they'll exceed 1,000 square kilometres in size, and the reason size is so important is if you imagine for every litre of diesel that we burn, we'll get back 2.8 litres of liquid CO2. So we're getting back a lot more liquid than we're actually starting up with. So we need vast amounts of storage space to deal with some of this problem. There's a huge amount of CO2 then gets put out there. So HyNet in the UK, so just to get a feel, so it's another project that is in the UK. HyNet has a storage capacity of about 130 million tonnes of CO2 is what they're expecting that they can sequester into that formation. Now they're looking to inject about 10 million tonnes of CO2 per year. Now that's the equivalent of taking about 4 million cars off the road or heating about 5 million homes. So these are pretty substantial projects, and they're things that can be deployed at scale. And you can see here there's multiple projects even just around the North Sea basin. Now there are much of what underpin oil and gas understanding and knowledge can be reapplied to CCS, but there are some key differences and some key new thoughts that are needed. So we need to think of this storage on a geological time frame is very, very important, and we need to think about the security of the sites is of the utmost importance. The technology that we have today to put the CO2 in the ground might not be around in 100 years' time or 1,000 years' time. We might want to choose sites for that reason that are harder to inject it into the formation because they don't naturally flow if there's any issues occur with them later on. On the previous slide, you would have seen that there's salt caverns are mentioned on there. They're not really a realistic storage site because of the scale that's required for CO2 liquid storage, but they might be part of a useful solution. And again, in the UK and Cheshire and other places, there are multiple salt caverns. These might be useful for unloading CO2 or even hydrogen during those phases. So it's a well-proven technique, mostly used for enhanced oil recovery in the US CCS. And as you can see from the amount of projects that you can see on this slide here, there's a massive amount of projects and infrastructure that are going to utilise some of the formations that we have in the UK. Crucially as well, our formations are in these coastal locations away from where people live. But they are close to densely packed industrial clusters, which makes the capture of the CO2 and then the piping offshore more economic and achievable. The other big advantage in the UK continental shelf is we have a lot of port facilities that are existing and being built out to handle liquefied gases. And in the future, we might well see the UK being an importer of liquefied CO2 waste, where other countries don't benefit from some of these storage sites, and potentially even an exporter of hydrogen because of the massive amount of wind that is going into the UK and the pipelines that go into continental Europe. So there is quite a lot of benefits from the UK basin being used for these types of processes. So we can go on to the next slide, please, for considerations into the storage sites. So we talked a little bit about whether saline aquifers or existing oil and gas sites, but weighing up that whether we use existing or new sites is important. So there's some other considerations to think about. So one of the advantages that I mentioned earlier about an existing site is the vast amounts of data that will be available, which makes the speed to get to the point of deciding whether a particular asset is viable economically and technically, makes that a lot quicker. There's also the potential to reuse some of the existing assets, but there's also a big negative there. So some of these existing assets might be legacy wells that penetrate the formation, and they may not have been abandoned in such a way that facilitates repressurization or indeed the use of CO2. And this is where new sites might come in that don't have those issues, but have more complexities with the speed in which you can get to a decision on a particular storage site as being useful or viable. So what might that look like? There could be, in an existing site, there could be some abandoned wells, which is quite typical with the next slide, please. With the conductors cut below the mud line, and that after looking at the records, it might be decided that we need to re-abandon those in such a way because the steel or the cement composition might mean that they're not suitable to get to the full economics of a site. You might otherwise have to lower the amount of pressure and therefore the storage in a particular site that we're putting this stuff into. So the alternatives might be that a costly intersection well needs to be drilled if we go down that route, which might mean that the site gets abandoned in its entirety. So you can go to the next slide, please. So some of the techniques that can be deployed are well known. I mean, since the 1980s, well before mudline hangers were introduced in the 80s, people have been doing tiebacks and re-entry work, but combination of existing technology, the tieback onto pipe, combined with existing but uncombined technologies such as magnetometers and seismic surveys with pilot holes to do well cleanup and stinger deployment, might be needed to run into these wells to re-abandon them for suitable CO2 deployment in the formation at a later date to make these fields economic, rather than just dismissing a legacy site simply because there's old exploration wells that haven't been abandoned in the correct way. Next slide, please.
Well, thank you very much, Ben. Neil, if you can go to the next slide, please. So touching on what Ben was saying, so if you're looking at using a platform to re-inject CO2 into a storage aquifer, a storage reservoir in an offshore location, so you may be presented with the choice of either using an existing platform or making use of a new platform. Now, so there's a key decision point to be made there. So why would you opt for a new platform? Clearly, overarching in all of these projects, if you're spending the time and significant expense for long-term successful storage of CO2, you do not want to generate a large CO2 footprint in the attempts to store CO2. You're looking to try and minimise your overall CO2, minimise the carbon footprint of that project in itself. So why would you go for a new platform? Well, clearly, because there isn't an existing platform. Option one, reuse. But if there's no platform available at the right location, if the platform is still in use, it may still be a producing platform that doesn't have the ability to swap to that point to go to an injection mode. Or you may have identified an ideal storage location, but it doesn't have any facilities on it. You may look to be working in shallow water depths where you're only needing, or the project may only need 1 or 2 wells for injection purposes, to last in the 5 or 10 years, as Ben was mentioning with the development he was talking about, that if you're injecting 10 metric tons a year, you may only be in place for 10 years until you have filled to capacity, at which point you're moving into you're no longer injecting, you're moving into a sort of a monitoring and maintaining mode. So the platform may only need to be in place for 10 years or 15 years. So if you're in a shallow water regime, you only need a few wells. And particularly with a new platform, if you can deliver the CO2 at the pressures you need to inject it, such that the top sides are very, very minimal, then a small new platform may be ideal. Flip side, clearly, why would you opt for an old platform? Well, key cases, if you're injecting into a depleted reservoir and the platform's sitting there, great. You may have a platform that has wells that are available to use and are in the right location. You're looking for multiple wells, more than 2 or 3, and the platform isn't so elderly that you believe you can extend its life for the duration of the injection project. And again, a key critical one, if you can only get the CO2 to the location at a lower pressure than is required for injection, and you need large rotating machinery, compressors, etc., to ramp that pressure up before you put it downhole, a larger platform with a larger footprint available for this equipment may be the necessity you need. So if we go to the next slide, Neil. So if we're talking about a new minimum facility platform for CO2 injection, so again, I'm basing this on our C-Swift line of platforms, which are small modular platforms that can carry from 1 well up to maybe 9 or 10 wells if at one end of the scale and the other. So clearly what you're looking for is a very small platform, very simplistic. If you're going to a new location, you will have to drill the wells. So make use of the facility, make use of the drilling rig and all of the infrastructure you're bringing in place to drill the wells, to install the platform, to lock the platform together in the water depths you're going to be dealing with. Again, if you're starting from a blank sheet of paper and you think this may have a life of 10 years, 12 years before you'll be shutting it in and moving to that monitoring and measurements phase, where you can design the platform for not only ease of installation, but ease of removal, ease of decommissioning, maximizing the reuse of that topsides equipment, so that you're not burning more CO2 in the recreation of equipment that you can reuse. And if you're going for a new platform, again, you would have a topsides that only has the equipment that is absolutely necessary for the task in hand. So shrink that topsides down, simplify it, make it as small as possible. Again, ease of installation, less steel, reduced carbon footprint. Again, next slide, please. So if we go to a position where we're transmitting the CO2 to the platform at the required pressure, we don't need to compress, we don't need to do any pressure changes. The topsides is literally an up and over topsides. It's a direct analogy of a simple little monopile gas producing platform that we've recently done in Trinidad, where it was an up and over topsides. Gas was coming up over the topsides and going to shore, and a new platform, we'd be looking at gas from shore up and over down into the reservoir. So the technology exists, the understanding exists to do these platforms. And if you're looking at a very, very simplistic topsides, you could then do, as we've done on that project, fully power the topsides with a combination of wind and solar. So again, you're minimizing that carbon footprint. You're making the whole development as sustainable as possible. You're not generating CO2 whilst you're storing CO2. You're trying to become neutral in the overall development. And clearly, that adds to the overall ESG benefits of the project as a whole, not just the platform in question. If we go to the next slide, clearly there'll be situations where you'll want to use an existing platform. I'll point out the platform in the image here is just there to represent a small offshore structure. Anything I talk about is not specific to that development. We're just using it as a general example. So clearly, again, if you've got a platform that's out there, it may have been producing for 10 years, it may have been producing for 25 years. You will have the benefit of it will be larger, it'll have more deck space for you to put equipment on, it'll have existing number of wells. And the reuse and the extension of life clearly has overall ESG benefits. You are making use of what you have in place. You are not developing from new. What you have to do is ensure that that platform can carry on for the life you intend it to have. So if it's been out there for 25 years and you think you might need it for another 10 years to inject CO2 into a reservoir, well, that's a 35-year life on a platform that may have only been designed for 25 years. So what do you need to do? Well, typically, if you move usage from a production to an injection, a CO2 injection facility, there will be a great deal of equipment on that topside that is now superfluous to needs. So mothball it, minimize it, remove it. If you can strip tons and tons of equipment off of that platform, you will be improving its structural response. You'll be benefiting from an improved fatigue standpoint, and that itself may give you the life you need. Or you may have to do additional engineering to look at strengthening in key nodes, key locations, just to give you that life moving forward. So, but again, this is not new technology. This is adoption of existing technology, existing capabilities. Measuring steel thickness at critical nodes in the jacket isn't something new. It's done all over the world at the moment. What you're doing is applying those known techniques, known engineering capabilities to provide that input mechanism to get CO2 into a reservoir. Clearly, one of the other benefits you'd want to do if you are stripping equipment off that topside, stripping it right down to the minimum, is you'd look to, where possible, electrify the topsides. Now, we know a lot of the people on this webinar, if they're involved in the energy production, they'll know that drive to electrify topsides is something that's already in place. It has overall benefits. If you can bring electricity from shore or from an adjacent wind farm, if you've got one of those handy, then what you're doing is you're benefiting both in terms of you're not burning diesel on the platform to generate electricity, you're providing all of the motive power you need to drive rotating machinery like compressors to get the CO2 in the ground, but you're reducing the carbon footprint again. But also critically, one of the most dangerous tasks in any offshore facility is getting people to and from that offshore facility. If you're removing the need to transmit or transport diesel out to simply generate electricity, you're reducing the overall risk associated to personnel transport, which is again a major plus point. The final point is, as an industry, we may well benefit from the fact that we have a number of these existing assets. We've been eking the life out of the structures in the North Sea and in other locations around the world that might be ideal for CO2 storage. We've been eking it out because in many occasions, we've not wanted to have that decommissioning and removal cost. We may actually now see the benefit, the upside of that, to use the assets that we've got in place, the assets that we've been maintaining to now, by that small change, small additional work to extend the life, make use of what we've got, reuse as far as possible, and lock CO2 into the reservoirs. So that's my last point, and I'll now hand you back to Ben.
Okay, so what does long-term CO2 management look like, and monitoring, measurement, and verification? You can go to the next slide, please. So, like like many oil and gas projects, detailed planning is absolutely essential, because we need to be able to demonstrate a detailed understanding of exactly how the asset is going to perform over time, and more importantly, for CCS, we need to demonstrate how that particular storage asset is going to perform once we've stopped injecting CO2 into it, and how it will perform over a geological time frame. So it's absolutely crucial. And during that baselining, to see how that asset will perform, it is absolutely essential that the engineers involved in the project are able to show how exactly what the characteristics are of that particular asset, and how it's performing. So things like how the CO2 plume will move through the formation is very, very important to demonstrate an understanding of how it's going to work, and the capabilities of that formation. The opposite, in a way, of an oil and gas asset, where you want to show how it's going to drain down, and the production rates you can achieve. What happens to the CO2 over its lifetime? So we're talking geological timeframes here. So it's really important, you know, what is the makeup of that formation? Is it of such a composition that actually over time that liquefied CO2 will actually enter the rock cycle? And what is the risk of a fault happening, or being in an area that might be active seismically, that might create some fault lines? What happens if there is something that happens there? Will it flow naturally? What are the injection rates you can expect to have? And what would be an acceptable CO2 level in the water column? And you can flip that round. What is the current CO2 levels in the water column? Because there's a natural state for this, and seasonality plays a massive role in that as well. So it's very important to have this critical geological timeframe thinking, and this is where when we look at who's responsible for it, well, there's some clear responsibilities during the injection phase, but those responsibilities become a bit grey as time goes on, once it becomes a storage site. So, you know, 10 years after cessation of injection, is it still the operator's responsibility? 100 years, is the operator, does that company even exist anymore? You know, so these are really important aspects to think about, and the technical risks as well. So any plans that are in place for a leakage on a particular site over a geological time frame, when does the risk dissipate for any leaks? And will technology still be available to address any leaks? It's no good having a plan in to drill an intersection well or a relief well or something to solve a leak if that technology won't be around in 50 years' time. So it might be better to plan a site where that risk is much less. So these are very, very important things. So the key thing is in order to prove that these desktop engineering studies, if you like, where we look at baselining a particular asset, that we understand it correctly, is to make sure that we fully understand the subsurface and the water column attributes that contribute to an answer. Either it's okay, everything's performing as we expected it to, or no, it's not, there's a problem. Next slide, please. So there's various different methods to allow this type of monitoring, measurement and verification activities to take place. Two of which really look at the water column. So dissolved gas sensors, looking at dissolved CO2 and how the CO2 plume behaves in the water column. This can be done via dissolved gas sensors that have been deployed in the past, and also through sonar techniques. So some of this technology has come from military applications that have then been put into the commercial world to look at these particular attributes. And then there's other methods that we can use to look at the subsurface conditions. So seismic techniques, for example, that have been deployed, where we can actually look at the formation before we start, and we can look at it again in the future once CO2 injection has begun. Now, all of these techniques here require a level of baselining that goes further than the initial desktop exercise, which is you would start with, like on any particular given development, looking at the information that you have available from a desktop study point of view. But then it's important to go out and take some physical measurements and to get to know the site better. So seasonality, for example, of CO2 levels, parts per million in the water column, fluctuate massively during a given season of the year. There might be naturally occurring bubbles that are happening and percolating up from the seabed. Perfectly natural, might not be a problem at all, but it's important that we know about these before we implement our equipment to look at this stuff. And equally, the seismic, there might be a need to repeat a seismic evaluation that covers the entire formation. And remember, we talked before about saline aquifers and the type of geographic sort of spread that these can cover. They're enormous. They might require various different nodes to listen in to get a picture of that formation itself, a proper picture of it, but then equally how that CO2 plume behaves and moves through it in the real world. Next slide, please. So there's various different experimental data that has been deployed, and there's various different positives and negatives that can be taken from each of these types of sensors that get put in place. Dissolved gas sensors, for example, rely on having proximity quite close to the source before some of the details of the parts per million become less meaningful. So we're talking a radius of maybe up to 50 meters. But that would need to be in combination with other sensor information to be able to understand that. And that's something that we've investigated as a company, applying additional sensors with aquadops, so we can look at the current direction and be able to compare that with other sensors to make comparisons against baselines. Sonar is another technique that's been deployed on some of these test sites. It's very useful, and it has a much wider range, maybe up to 500 meters in radius. But some of the downsides are we can see the bubbles, but we don't necessarily know what they are, so they might not be anything to worry about. And of course, if there's no bubbles, it can't see it. Now, there's a significant area of unconsolidated material beneath the seabed where the CO2 could indeed dissipate and dissolve into the water column long before it gets to the seabed, so you may not see anything at all. And then we come on to the seismic subsurface equipment, and this is probably one of the areas that plays a really fundamental role, because the two water column methods are essentially a fire alarm that there's a problem, we've got a leak and it's happening. The subsurface technique of repeat seismic, which is being done in various different locations at the moment, and there's fibre optics been deployed in Australia with repeat seismic to track a gas plume by a company right now. And that's a very useful technique, because it demonstrates that desktop engineering that has been completed has shown that we understand the formation and that it's moving through in the way we expect. And if any anomalies come up, we can move on from there. Next slide, please. So what could we do? What do we need for these systems? Well, some of these systems we can put nodes very close to where we've drilled to inject in these new wells potentially that get put in. But because of the size of some of these areas that we need to cover, there might be more remote locations. So the system that Aquaterra has been working on is what we call a host. which is essentially a power system and telemetry system between the seabed and surface that can then send data back to shore. We believe this might play a part in the carbon capture world for supporting monitoring, measurement and verification, be that through the water column with the addition of dissolved gas sensors or even sonar, through to subsurface seismic fibre optic lines being able to be installed into the node location, with the interrogator systems stored in the buoy itself, with the data being sent back to town as the seismic surveys are repeated, and they're compared against baselines. Also, permanently installed seismic can pick up microseismic events when there's no sound energy sources introduced, or detect temperature leaks at these levels. So could be quite an important technology in the mix for these particular types of site. But again, as I talked about, CCS not is being an important part of the solution. These sensors, be it through the water column or subsurface, not one of these is the complete answer in my view. It's going to be a combination of these sensors are required to give the public and regulatory bodies and the operator themselves confidence that the engineering work has been done well enough to demonstrate that we understand how it will function, and that there's enough equipment there to be able to sense and detect any issues that might happen. And our final layer of defense is that once it enters the water column, we want some sort of fire alarm to tell us to go in and act. And that might be a combination of deploying autonomous underwater vehicles to do further investigation, or to look at other methodologies to further refine that. Next slide, please.
Sorry. Sorry, Ben. Forgot to unmute for a second there. Thank you everyone for listening in. And before we go to the Q&A session, just obviously the key takeaways from the points that were raised so far is, we talked about, the challenges of storing CO2, in that, you've got challenges from legacy wells, existing infrastructure. Is the geology right? Isn't it right? And these are not unique. Sorry, these are not common. There are unique issues in each location that would need to be identified. When we talked about new platforms, that we can transfer exactly the same skills and learnings from what we've been doing at the moment for extraction to injection. For old facilities, weight, simplification, electrification, and life extension, which are all intrinsically tied together, are the key for using existing assets. And as Ben sort of covered there at the end, there is no overriding solution for CO2 management. I think the key point you mentioned there is you're talking geological time, a period over which not one person will be able to sit and manage and interpret the data. So you need to look at the combination of sensors and the techniques you're planning and use, and make the system open and adaptable for new technologies that will come in and improvements along the line, such as AI, machine learning, where the machine itself is comparing the data, making decisions and reporting back to the people taking part in the monitoring. So I'll now hand it over to you, the people on the webinar, to ask any questions that you would have, and back to Neil as well.
Okay, thank you very much, Stuart and Ben, for a very interesting and insightful discussion. We have had several questions come through, so we'll just get started. First one, what's the acceptable CO2 leakage rate before remediation on the legacy exploration / appraisal wells need to be done when utilising depleted gas reservoir as CO2 storage?
Okay, straight in there with a very detailed technical question. Now that is the subject. There has been some levels that have been advised by the Norwegian regulator bodies, and I don't know the numbers off the top of my head, but they are kilos that they talk about, kilograms of CO2, which I think in some respects might be an unrealistically low number. There's a lot of work going on at the moment in the UK in particular and internationally to put together a set of standards which will undoubtedly cover what constitutes an acceptable leakage rate. My own personal opinion is I think that's important. I think that there absolutely has to be some sort of standard that is covered for this. But I think from a public point of view and a perception point of view, that is that number needs to be zero pretty much. And as I talked about earlier, this is a geological time frame. So I think we don't want something that is leaking for 1,000 years or something like this. But we must also remember that the consequences of CO2 leaking out is it's dissolving into the water column. It's not as immediately apparent and disastrous as, say, a hydrocarbon leak into that same marine environment. And these could be at quite low levels, could possibly be acceptable, although definitely not desirable.
Okay, thank you very much, Ben. Second question, would the CO2 migrate through formations more easily or less easily than natural gas, or do they have similar properties?
Sounds like another one for me. The CO2 when it dissolves into the water makes a dense briny solution. So the percolation of it coming up and out of the formation in some respects might be beneficial and behave in a more beneficial way than gas, which is expanding constantly as it's coming out. So there is a chance that some of these formations, depending on the location, the behavior might be better. But that makes detection harder, and this is where it comes into the effect of knowing formation and being able to see subsurface as well, how that plume is behaving is absolutely essential. Stuart, I don't know if you've got anything to add.
I would just say it's a hard question to answer overall because it will depend on any potential interaction, as you've mentioned, Ben, between the CO2 itself and the geology and the formation. And different formations will react differently to the CO2. I mean, CO2 as a molecule is obviously carbon, 2 oxygen molecules as opposed to CH4. So we're talking about fairly small molecules. So you would imagine that gas would percolate slightly more easily than potentially a CO2, as you're saying, if it starts to sort of effectively stick and lock into the formation more.
And I think most of these storage sites as well are planning to have it in the supercritical or liquid phase as opposed to pumping in as a gas. I think just to clarify that as well, I think that's quite important.
Okay, thank you both. I think we have time for one more question. So this one is, are there any notable environmental concerns regarding sonar, seismic, and more broadly other MMV techniques?
That's another one for me. I think you're going to have to find one for Stuart in a minute. Yes, there are. So sonar, potentially, they use very, very high energy sources for the sonar that can potentially be a very, very large decibel level, which could potentially be considered as a noise pollutant in the water column. That's why I mentioned that there are some limitations potentially with sonar. What you don't want to do is have an array of these over several hundred or even 1,000 kilometers in area where you disrupt marine mammals because of the noise. There are some mitigation measures that some of the sonar suppliers put in place, such as they'll ramp the energy up from they won't just instantly go to a very, very high intensity energy source. They will ramp it up gradually to, if there is a whale in a very close proximity, for example, it can then, it will gradually ramp up to a safe distance. But I think my view is that dissolved gas sensors are probably, with combination of tidal and current data, is probably the way to go, combined with subsurface seismic, because of some of these issues and some of the others I mentioned. Repeat seismic, again, there is an issue where we're putting the sound sources in, but the dissolved gas sensors are pretty passive, and I don't really see there's too much of an issue with those.
Yeah, I was going to agree with what Ben says. I think that a lot of the sensor technology, with the exception of sonar, is passive. It's sitting there waiting for things to happen, and they run off relatively low energy levels. With sonar, clearly, much like if you're doing exploration work or doing any offshore stuff at the moment, you would time the seismic activity, so you're out with any migratory, sort of sea mammals. You would have a watching technology. If you've got sensors down there that are picking up CO2 particles, or using that to measure stuff in the water column, they're probably capable of noticing a wheel.
And just to go back, I guess just to reinforce that a little bit more, I think one of the key things with, say, permanently installed fibre optic lines for the seismic going forward, they don't necessarily need an energy source to measure microseismic events, which could lead you to see maybe issues forming in the plume. We do need an energy source to see what's happening subsurface and see that plume moving through. If we look at some of the experimental jobs that are ongoing, say in land in Australia, they use flapper plates on the ground to introduce that energy source. There's possibility that these types of things could be used in a marine environment as well, because we're talking about many node sites. As opposed to nitrogen guns or anything like this, what would be more traditionally used. Because we're repeating the seismic job, the seismic work regularly. I think the one in Australia is literally every single day. That's probably not needed for this, but it's going to be regular stuff. We want to have a simplistic way of introducing that energy source that is compatible with the environment that they're installed in. Yeah,
and again, I think I touched on one of the points I made earlier. When you're dealing with this level of time and elapsed time, it's a bit like censoring equipment offshore we've got at the moment. You've got stuff there that will measure things that are happening instantaneously, and a computer will react because humans can't act that fast. There's a period over which an event takes place that people are best placed to react to it. They can take the information in, they can make a decision, they can react. And then there's time beyond that people can't, because you're talking geological years, etc. So as Ben's mentioning, if you're measuring seismic activity continuously or very regularly, and it measures a microseismic event, and then at some period later a plume appears, or a leak, or X or Y, or something in the background changes, human beings will not be best placed to interpret that data. You will need machine learning, you will need an AI suite gathering all this information and looking for patterns, reporting on those patterns. And when it's, when the computer, and I hate to say computer says yes or computer says no, but when the computer or the system identifies that an issue may take place, that's when people come back into the picture, because they're best placed to understand what to do to correct, what to fix, how to go about doing it. So, if we are talking about hundreds, thousands of years of ongoing measurement, that's numerous, obviously, lifetime people, companies, assets. You'll need that data set handled by something that doesn't notice the passage of time.
Okay, that's all we've got for today, unfortunately. I'd just like to thank our speakers, Ben and Stuart, again, and everyone for tuning in. We hope you found it useful. We will be emailing around a recording of today's presentation, just in case you'd like to listen to any parts back. And I should say sorry if your question was not read out today, but you can contact us using the details on the screen at the moment. If you do have any further burning questions, and we will try to answer them as best we can. Well, that's all we've got for today, and we hope you can join us for further discussions in the future. Bye-bye for now.